तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So far we have been looking at numerical solutions of differential equations of the form y prime equal to f of x comma y, first order differential equations with some boundary conditions specified at x equal to x naught, that is the in the beginning of the interval. And we looked at 3 different methods, actually 4 different methods, 2 of them being on the Runge Kutta scheme. And in these methods we wrote y at x plus h as y of x plus f into, that is y prime at evaluated at x comma y into h. So we wrote these methods. And so that is one method which we said Euler's scheme, and then we can go starting from x0 to the other end of the interval which you are interested in. Another method which we looked at was to evaluate what is called a predictor, okay, which at x plus h from this scheme, and then use a corrector step to get the correct value as f of x y plus x plus the derivative evaluated at x plus y and the derivative evaluated at x plus h and y 0 at x plus h divided by 2. So that is another scheme which we looked at, and we said that we could do this iteratively and the predictor corrector scheme to get better accuracy. And the second order Runge Kutta method which we looked at was exactly this one. So this is predictor corrector and second order Runge Kutta, in which we evaluate the derivative at 2 points, one at the beginning of the interval and one at the end of the interval with the predicted value of y, predicted value of the function, and then taking the mean of that derivative. And in the scheme where we looked at the fourth order Runge Kutta, so then we wrote here y x plus h as y at x plus 1 by 6 times k1 plus 2k2 plus 2k3 plus k4, and k1 was f of xy, and so k1 was f x y, f evaluated at x and y, and k2 into h, that is what we wrote it as. So k1 was h times f of xy, and k2 was h times f evaluated at x plus h by 2 and y plus k1. And similarly k3 was h times f evaluated at x plus h by 2 and y plus k2. And then k4 was h into function evaluated at x plus x, that is the derivative evaluated at x plus h now, and y plus k3. So this is a scheme which we have learned so far. So we want to solve equations of this type, first order differential equation with the boundary condition specified at the beginning, that is initial value problem, and we looked at the Euler scheme, the predictor character scheme, and so this is basically the predictor character scheme or the second order Runge Kutta scheme, and then a fourth order Runge Kutta scheme. So this is what we have so far looked at. Now the question would be that if I want to solve differential equations of higher order differential equations, and then what would I do? So like how do I proceed in the case if I had to solve a higher order differential equation? That is, if I had to take differential equations of the form, let's say y double prime is equal to some function of x, y and y primed. So that is now the right hand side is a function of x, y and the first derivative, and so this is the second derivative, y double prime is the second derivative. Let's say this is a equation of order 2. So let's say I want to solve an equation of this form between some interval x going from x0 to x going from to x1. Again, we were only interested in the initial value problems. That is, we could say that y is specified at x equal to x0 and y prime is specified at x equal to x0. Okay, so now this is a second order differential equation. So you need two boundary conditions, and so both boundary conditions are specified at the initial value. Okay, that's called an initial value problem. Of course, we could have problems in which one condition is specified at the initial case x equal to x0 and the other one is specified at the other boundary. Okay, so then that will become a boundary value problem. We can use the method which we learn here to solve problems of that type. We will discuss that at the end of this section. Okay, so for time being, let's concentrate on this issue, that is how to solve an equation of this form with the boundary condition specified at the initial value. That is the second order differential equation with boundary conditions specified at the initial value using one of the schemes which we have learned. Okay, so we would use a Runge Kutta scheme for solving this equation. So what we do is we split this into two first order equations. That is, we would write y prime is equal to z, and then say y double prime, so now y double prime, that is z prime, so that is z prime is equal to f of x, y, z. Okay, so that will be our equation. So now we have two equations. Instead of one second order equation, we have two first order equations. And now we have boundary conditions for this as y at x equal to x0, and then we have boundary condition for this which is z at x equal to x0. So we have boundary condition one boundary condition for each of them, and then you can solve this equations. Okay, now that's a scheme which you will be following here. So I summarize that here. Okay, so we want to, let's say for example, here is an example of one differential equation of that form. So you have a second order differential equation. So it's a d squared y by dx squared plus a dy by dx plus cy plus d into x equal to 0. So now we have a differential equation of this form. So this is a second order differential equation, and then we want to solve this with a boundary condition that y at x equal to x0 is y0 and y at y prime that at x equal, that is first derivative dy by dx at x equal to x0 is c. Now we have some boundary conditions. We want to solve it from 0 to x equal to x0 to x equal to 2 for example, some x equal to some x value to another value at which is given as 2 in this particular example. So how do we go about solving this? So we said that we can split this into two first order equations, right? These two first order equations are now given by this dy by dx is equal to z, and dz by dx now is to become az plus cy plus xt. Okay, so let me write that. There is a minus sign probably. So we will write this form. So this is equation. So it's that. So our equation was d squared y by dx squared plus we had a dy by dx plus cy plus d into x is equal to 0. Okay. So, we will write this as now we are going to write this dy by dx, that is y prime. We are going to write that as z, okay, and we are going to say we are going to say z, so dz by dx is equal to minus a, so that's z, right, minus of az plus cy plus d into x. Now we have boundary conditions given as y at x equal to 0 is equal to y0, right, and y prime, that is z at x equal to 0 as okay. Now that's our boundary conditions. So now with this we have to now write, so how do we solve this? We would write, we say y at x plus h, right, we will write that as we have done y at x plus, we want to solve this, right, the z is the right hand side, so then I would write this as 1 over 6 times k. Let's do a second order for to begin with. We'll then solve this for fourth order also. Okay, so I will write it as kz1 plus kz2 by 2. So let's do it first, second order first. Okay, so now that's what you would do, right? So that's where kz1 and kz2 by 2. That's what you would write. Okay, and then similarly I would write z at x plus h will now be equal to z at x plus half times a into, now again, so we would write here, I would write it as k y1 plus, sorry, I made a mistake here, k y1 k y2 and k z1. We would write, use notation ky for the y thing and kz for the z1, kz1 plus kz2 by 2. Okay, so that's what we would write. So now this is the two equations which we have to solve. Okay, so now the point is to find out what is this ky1, ky2, kz1, kz2 is. Okay, that's what we are going to now write down. So let's summarize this once again. So I want to solve this equation, these two first order equations. Okay, there's actually a minus sign there. Okay, using a second order Runge Kutta scheme, and I would just write it as y at the next point as y at the first point plus this ky1 plus ky2 and kz1 plus kz2 for the z1. So ky and z would go by these two quantities. So y will proceed using ky1 and z will proceed using ky1 and ky2, and z would proceed using kz1 and kz2. Okay, so starting from the initial value, we would compute the next values using this, okay, second order Runge Kutta or one level predictor corrector scheme. So now the question is, what this ky1 would be, and how do we write that ky1 as? Okay, so that's, so remember the z next step is z plus kz, okay, and the y next step is y plus ky. Okay, so now let's compare this with the first order equation which we wrote. So when we write dy by dx as f of x comma y, okay, our k1 was f of x comma y and k2 was f at x plus h and y plus ky k1. Okay, so that's what we had written as k2. So now we do exactly the same, but now there are two such equations. So we have to write now ky1 and ky2 and kz1 and kz2, etc. Okay, that's all we have to do here. Okay, ky1 as f at x comma y, if it's in y, this is in y, and we say ky2 as now f at, in general it can be a function of x, y and z, so we'll say x plus h, right, y plus ky1 and you can have z plus k z1. Okay, that's the only difference. So you see this second equation here, okay, can be a function of x, y and z. So x, y and z. Okay. So to evaluate ky2 we were to first get kz1. Okay, so we can't evaluate this in one shot. Okay, so we have to do that in the series. That's the only thing which you have to be careful about. So when we compute this one here, so let me compute this for this. So we want to do this. Okay, so first we have to get kz1. So we'll write it in this form. So we get kz1. So our idea is to use this, right? We want to evaluate z at x plus h and y at x plus h. So to do that we need kz1, kz2, ky1, ky2. So the way we are going to go about this is first to get kz1. So that is, in this case, is just z, right? So that's just that. The function, this is the first equation, dy by dx, and that is equation 1 and this is equation 2. So let me write that carefully. So I'll say ky1, that's the right hand side of dy by dx is equal to that is z at x, and so that's first point. Okay, x equal to 0, and then I would do kz1. So then I do kz1, which is this quantity, which would be minus a z plus cy plus dx. Okay, so that will be the second quantity. So the way I go to do is that. Okay, so first I compute ky1 and then kz1, and then I will do ky2. Okay. Now this I can compute because I am going to say it is, so we are going to use an h here for everything. So minus h times that. So minus, plus h times z plus kz1. That's what we are going to use to compute ky2. So we can do ky1 and then we have to do kz1, but before we do ky2 we have to do kz1 because we need kz1 there. Okay, and then I can do kz2. Okay, that is equal to now minus h times a plus kz1 plus into and c times y plus minus h into a times z plus kz1 comma plus c into y plus ky1 plus d into x plus h. Okay, so that's our kz2. Okay, so now we have ky1, kz1, ky2 and kz2. So remember that before we compute ky2 we have to compute kz1, right? And before we compute kz2 we need ky1. So we have to always do the one level thing and then go to the next level in this when you split the equations into many first order equations. So you could do this for any number of any order, that is if you could do a fourth order equation and then you will have 4 such first order equations, and then you will have, let's say, k1, k2, k3, k4 for each of or in this second order case you will have k1, k2, k3, k1 and k2 for each of these equations. Okay, so the care should be taken in just in doing the, and when you program it, the correct order, it has to be computed in the correct order. That's the most important thing, and that's what one can make mistake in this particular case. Okay. So let me repeat this here. Okay, so you had to solve these equations. Okay, that is as yn plus 1 is yn plus ky1 by 2 plus ky2 second order, and similarly for z. Okay, so when you compute, as you can see, first you compute ky1 and kz1, okay, and then you compute ky2 and kz2, okay, and then we'll proceed in this fashion. Okay, so this h can be written either along with the k or with the on the right hand side of this function. Okay, so since we are not included h here, so we have to have a h on these equations. Okay, so that's a general procedure, and you can see that we can do the same thing for the fourth order case also. So we'll see that in a program. Okay, so this is a program. This program looks a little complicated, but in fact this is extremely similar to what we have done in the earlier case, that is for the fourth order Runge Kutta. but now we have two equations. Okay, so let's just straight away go to the function. Okay, so the function which we are trying to solve, okay, is the following. So now I split that function into two first order equations. So let me write the second order equation and then split that into two first order equations. So the quantity which we want to solve is the following. It is y double prime is equal to we're going to write 5 minus 4y, 5 minus 4y plus 5 times dy y primed. So that's the equation which we are going to solve. Okay, so 5 minus 4y minus 5 y primed. Okay, that's the equation. So we are going to write this as two things. Okay, we are going to write y primed is equal to z. Okay, and z primed equal to 5 minus 4y plus 5z. So in the program, in general, we could have an nth order differential equation and n such first order equations. Okay. So since our aim here is to solve these things numerically, we should also see how we develop an algorithm for this. So one thing which we will do is that when you have an nth order equation like this, the solutions will now be both nth order equation like this, and we will have a solution of y and y primed, y double prime, all the way to y n, right? So that's n minus 1. So that will be our solution set. Okay, we'll have all of them as a function of x. Okay. So we call them as y0. We'll put them in an array, and this is called y0 and y1, y2, etc. to yn minus 1. So that's what we will do in the program. Okay. So remember, when you have a higher order equation, so I write each of those solutions as the elements of an array. Okay, so now this is the y0 is y1 is the first derivative, y2 is the second derivative, etc. So our equation in that language will transfer this z is now y1. So now my equation is actually y prime equal to y of 1, right, and y1 prime is equal to 5 minus 4y0 plus 5y minus actually minus 5y1. Okay, that's the way we would write. Okay, so y0 is y and y1 is the first derivative of y. Okay, that's what we would write here. Okay, so that's the way I have written here. So this is the first equation. This is the first derivative. Okay, so you have two derivatives now. That is, the first derivative is just y1, and the second derivative, that is the derivative of y1, okay, is given by the derivative of y1. That's the second derivative is given by 5 minus 4y minus 5y1. Okay, so that's what the equation is we are going to solve. Okay. So now we have to have the boundary conditions. The boundary conditions are specified in the main program. Okay, so that's my main program here. Okay, the main program, we have the upper limit and the lower limit. So I'm going to solve this with the limit x equal to 0 to x equal to 2. Okay, so now what we're going to solve this one. So we're going to solve this one from x equal to 0 to x equal to 2. Okay, so that's what we're going to do. And then now we have, as I said, y is now, I got two. So y, x and y are pointers, and this is now I have two elements in this array. So I am getting a 2 here. So the two elements here in this array, y0 and y1, because my order is 2. So I put that m as 2. Okay, that's my order. So this specifies my order. And n would be generally the number of points I would use to solve. But I'm going to do this in this particular program using adaptive step size. So this has everything now. So so if I can change the order here, okay, and then this program would work for any order of the differential equation, okay, provided you give all the boundary conditions at the initial position, and it will run for using adaptive step size. Okay, so let's look at that. So now we have the boundary condition specified here. The boundary condition is y0, y1 both are 0. Okay, that is, so we have x, so y at this point y is 0, and this point that z is 0. Sorry, at x equal to 0, y is 0, z is 0. Okay, so that's what we have. Okay, that translates in this language to at x equal to 0, y of 0 equal to 0, y of 1 equal to 0. Okay, so that's our boundary condition. So now given that boundary condition, I can start from x equal to the lower limit and go all the way to the upper limit. So I start with x equal to the lower limit. This is x is a pointer here, which gives you that. Okay, so now I call a Runge Kutta scheme of order 4. Okay, and I pass the order of the equation, right? And this is we saw in the last class that this is the step size which we suggest. Okay, so h is the step size which it suggests, which actually it asks for here. Okay, the program asks you to enter the suggestion for the step size, and then it reads the step size from the screen, and it will modify the step size by using an adaptive step size algorithm. Okay. So here is the step size, and here is the pointer to the function which contains all my derivatives. Okay, so now this order will be passed on to, will be important in dimensioning the derivatives. How many derivatives are there? So if it is 2, m is 2, then there are 2 derivatives, and x and y are the values. X is the value at which we want to now do the calculation. So we go from x to x plus h, okay, and y is the solution set which will be returned, and hn would be the distance to the next step. Okay, the adaptive step size would tell you what the next step should be used as. Okay, so that's what we will put that back and go back. We'll put that as h here and goes back here and goes to the next x value. So this program would return to us the next x step. Okay, and so if you give x0 y0 to start with, here we give an x0 y0, okay, and it returns the solutions at x plus h and the y values at x plus h. That is y and y1, y0 and y1. That is the function and its first derivative, because the order is 2. So that's what this program would do. Okay, that's the main function. Okay, so now this just calls this program. Now in this program, now we have to have the y's, which is again the same dimension as the y's. Okay, and then now we have the derivative here. Now the derivative dy dx is also now which I call the dy dx is a derivative. This also is now an array of dimension 2. So that's one thing you have to remember. Okay, so now this dy dx is the derivative, is the array of dimension 2. That is the derivative of this equation and the derivative of that. Okay, so now this derivative is called dy dx0, and this derivative is called dy dx1. Okay, so these are the 2 equations you are going to solve, right? Okay, so this left hand side is called dy dx0, and this is called dy dx1. That's what we are going to use. Okay, so basically dy dx0 will appear in all k's ky ones. Okay, so that is the first derivative. So all the ky ones that will enter. Okay, and the kz ones it will enter as dy dx2, dy dx1. So okay, so now let's see that. Okay, so now again, so we are going to use an adaptive step size, as I said. Okay, so here we will now start with these values, right? So we have whatever x value is given to this program. So let me write the scheme here. Okay, so remember, so we want to start from x equal to 0. So we start from x equal to 0, and we are going to give so in the main program. So the main program, what it does is it takes so main program just takes an x and y value. Okay, so it takes an x value and y at that x value and y prime at that x value. Okay, that's what this program is going to do. Okay, and it is going to call from this main program. Okay, and it is going to call this Runge Kutta 4. Okay, that's I call RK4. So Runge Kutta 4. Okay, and then so this program would calculate y at x plus h and y prime at x plus h. Okay, so it would calculate that given this. Okay, so now to determine this h, so we also pass an h to this program as a guess value, right? But this program would actually call, would actually look for, it will return to this one, okay, this values y at x plus h, y prime at x plus h, and an h next. Okay, so h next, which I call hn. Okay, all these things are returned to this. Okay, and actually x plus h. So that will be returned to this. And now what we do here is to now replace these quantities, which is going to pass on to this, as these quantities. That is y at x plus h and y prime at x plus h and x by x plus h next. Okay, and then it goes back here as the initial value, and then it will compute the next step and comes back here again. Okay, that's what we want to do. I hope that's clear. Okay, so that's what is done here. Okay, so now we have got this y0 y1. So remember, each time this program is called, that is each time this RK4 Runge Kutta 4 is called, okay, it gets a new x0 and y0 value. Okay, so that is from the main program. So the main each time this calls this function, okay, it gets a new value of x and y. Okay, so that's what it's going to use for the next time step. Okay, so this gets x0 y0 as a value, and it just simply writes it onto a file, and it goes back and calls it again. Okay, so every time it's called, it's going to call with the new x0 y0, that is x plus h y and y at x plus h, and then x plus 2h and y at y0 and y1 at x plus 2h, etc. So for this program, it's always getting x, y0 and y1. Okay, so for this guy, okay, this guy which does the RK4, it's always getting these values at x and y at x and y prime at x. Okay, what is that x keeps changing as we make each calls. So that is the part here, and then we store that thing. Okay, so and then we will, as we have done in the first order case, the first order differential equation. Now the only change here is that we have, instead of y alone, now we have y0 and y1. Okay, so now we have the initial values given as x and x, that is xx is the x value at which we are going to evaluate this, right? And then y0 at that point, which I call y01, because y01 is stored as y0 and y11 is stored as y1. Right? And then I'll go here, and then I call this function called derivs. Okay, remember, this is exactly the same as the first order differential equation case. Only thing is now this derivs, which is a function which we looked at, now returns two derivatives, dy dx0 and dy dx1, and we have passed two y values, y0 and y1. Okay, that's the point. So now, and then using that y0 and y1 and dy dx0 and dy dx1, okay, we compute the new values of y0 and y1. Okay, so now this idea is to do, here we are doing a fourth order Runge Kutta, and we want to compute y of 0 as y of 0 plus 1 by 6 times ky1 plus ky2 plus ky3 plus 2 ky1 plus 2 ky2 plus 2 ky3 plus ky4. Okay, that's what we are going to compute. So we do each step. So when we compute ky1, I will update my y0 as y0 plus ky1 by 6, and similarly for y of 1, I will write y of 1 as 1 by 6 times now kz1 plus 2 kz2 plus 2 kz3 plus kz4. Okay, so now this is the dy dx2s. Okay, these are dy dx1 zeros, and these are dy dx zeros, and these are dy dx1s. So again, when I compute this, I will compute ky1 and kz1. That is dy dx0 and dy dx1. I will update this. I will do this step first, and then I will do this step. Okay, then I go around and compute ky2 and kz2. So every time I compute this thing, I update my y by adding that part into the y0. Okay, so that is what this program is doing. So first step is to compute ky1 and kz1. That is returned as dy dx0 and dy dx1. Okay, in this thing. Okay, there is an array here. So the advantage of writing this in the array form is that you can say extend this program to any order by just changing that order m, setting m equal to 2, 3, 4, etc. So then this array dimension would automatically change because we have dimensioned it as m plus 2 here. Okay, so the array dimension will automatically change. So that's the first step, and then we go from x plus h by 2. Okay. So that's the next step. Okay. And then we'll compute now ky2's and kz2's. That is again the derivatives at that values. Okay. So that's what we are going to compute there. Okay. So now we are updating the y values. So now if you want to compute kz2 and k, remember if I want to compute kz1 in this program, in this is the equation which you are going to solve, right? So ky1 is z plus ky2 is z plus kz2, right? So we'll write that again here. So when I want to compute this, so what I need, so I computed first ky1 and kz1, okay, and I added that into this part, and that's finished. Okay, so now I want to compute the next step. Okay, so that is kz1, ky2 and kz2. Okay, so remember ky2 is actually in this case z plus kz1, right? That's what ky2 is. Okay, this is ky2. What is coming as y here is the ky2, so that is ky2 is that dy by dx is equal to z. So this equation has the ky's, okay, and this solution of this gives us the y's. Okay, solution of this gives us the y1, that is a z. Okay. So this has the kz1, kz2, etc., and this will be ky1, ky2, but the right hand side of this is just z. So ky2 is z. Okay, so ky1 was z, and ky2 is z plus kz1, and kz1 was 5 minus 4y minus 5z, okay, 5z, and now kz2 would be then 5 minus 4y plus ky1, right? So that is here, and minus 5 into z plus kz1. Okay. So in this program what I do is I pass this new y value, okay, and the new z value into the function, and it will return the right hand sides, okay, for both ky2 and the kz2. So that's what it would return. So I just computed that y value, y0 and z, that's y, this is y, and this is z. Right? Y1 is z and y0 is y. Remember that. Okay, so now that has been updated as derivative by 2 and this divided by 2. Okay, sorry, that's in the case z2 there is a half here. So that's what we are doing. So we compute this at the case z2's, okay, and by passing this function, this as a new y value into the function which returns the derivative. So I have a function which just simply returns the right hand side of these two equations. To that equation now I pass z as that and y as this, and it will return the right hand side of these two as dy dx0 and dy dx1. Okay, so that's what is done here. Okay, so I updated my y0 and y1, okay, and yy0 and yy1, okay, and then I pass that into this function, and then it will return the dy dx0 and dy dx1, okay, and then that will give me the derivative, and I use now this equation, and I add this term now to the y value, okay, that is ky2 by 3 and kz2 by 3. Okay, so that's what I am doing here. Okay, that's what's done here. So I'll update that thing again, and then I do this similarly for ky3. Now this step is straightforward. So now this is same as this. Now I do for ky3 again, update my yy and yy0 and yy1. Okay, call the derivs to get the derivative, and update my y0 and y1, and similarly for k4. And then it's the first loop when I do this, okay, I store them, that solutions I got as yn0 and yn1. Okay, so that is my predictor. Okay, in that some sense it's my predictor, okay, and then predict this predicted value with step h, and then I reduce my step to h equal to h by 2 here. Okay, I still reduce my step equal to h by 2, and I do the same thing now for two loops, that is h by 2 step and x plus h by 2 and x plus h, and I get the new y values as we saw in the last class for the case of a first order equation. Same thing we repeat for the second order equation for with y0 and y1, and the earlier case it was only y0, that's the only difference. Okay, so and then we compare the error which we get in both cases. Now there are two functions, so yn0 minus y0 by y0. So remember yn0 is what is the y value obtained to at x plus h using one step, that is go from x to x plus h in one step, and y0 is a y value obtained by going from x to x plus h in two steps, as x plus h by 2 and then x plus h. Okay. Now these two step value, we will compare these two values, that is yn0 minus y of 0 divided by y of 0, the absolute value of that. So then similarly for y1, okay, so and then I add this and construct an error function there. Okay, I construct the error function here in this way, okay, and then I look at my error is less than my tolerance or not. Okay, if it is less than the tolerance, I increase the step by 2 times the h value which I used. If it is greater than the tolerance, I reduce the step size further to h by 2, okay, and I restart the whole program, the whole thing again, okay, the whole calculation again. So that is something which we saw in the last class, okay, and then I return the y values and the x values, the x next values to the main program, and the main program will call it with the new x values and the new y values, okay, and the process would repeat. So let's and then at the end we are solving an equation of this form. Remember that is d squared y by dx square is equal to 5 minus 4y minus 5 dy by dx. So let's look at this. We'll just run this program and then see that. So that is okay. So now we need to pass the step size. The order of equation is 2. Okay, so the second order equation, and the upper limit is 2 and the lower limit is 0. So it's solving from 0 to 2. So I would just enter a step size, let's say 0.5, okay, and it has solved that. Okay, now we'll just plot that function. So we get the data file we get is actually adaptive solution.dat. Okay. So we'll plot that. So we have now in the solution set we have now this. Okay, so I should just show you that solution how it's written. Okay, now the solution is written in this form. In the main program, I write the solution as x, that is x value, and the y value and its derivative. Okay, so if I use 1 and 2, then it is x versus y, and if I use 1 and 3, that x versus y prime. That's the derivative of y. Okay, so the complete solution, as I said, a second order equation. The complete solution means actually obtaining both the function and the y as a function of x and its derivative as a function of x. Okay, that's what we. Okay, so now here is the solution of the equation. So now this is x versus y. Okay, I'm plotting x versus y, and this is the y value as a function of x. We can also plot the x. You can also plot the next part, that is the derivative. So that will be using 1:3, that is x and its derivative. Okay, so as I said, the solution was written as first column is x, second column is y, and the third column is the y prime, that is the derivative. Okay, okay, now that's the derivative. Okay, so you can have the solution the solution to function, that is the y value and its derivative. As you can see, the derivative increases here and it decreases here because this function is saturating to some value here. Okay, so now that's the solution of the equation of this form, that is y double prime equal to 5 minus 4y minus 5y prime, or the second order equation with the boundary conditions specified at the initial value x equal to x0. So now we end the discussion on ordinary differential equations here with just one more point, that is that so far we have only seen how to solve the first order equations. The initial value problems. Okay, we saw how to solve nth order equations, nth order ordinary differential equations as an initial value problem. In the case where some of the boundary conditions are specified at one point and other boundary conditions are specified, other m minus n boundary conditions are specified at the other end. Okay, for example, in this case you could have the one boundary condition specified at x equal to 0. Let's say, for example, y is specified at x equal to 0 and z is specified at x equal to 2. Okay, that is, or y prime is specified at x equal to 2. Okay. In that kind of cases, which is called the boundary value problem, we can still, in some of the problems, we can still use these techniques. Okay, and those are called normally the shooting method, okay, in which what we do is we again convert this into an iterative scheme. Okay, so we start with, so let's look at a particular example. So let's say we were given x equal to 0, y equal to 0, and x equal to 2, y equal to some y1, okay, some z equal to z equal to some z1. That's the boundary condition given. Okay, it could be even y. Okay. So, but let's say one end we are given the derivative, and other end we are given the y value. Okay, it could be that both ends the y values are specified. Anyway, one boundary condition is specified at x equal to 0, another boundary condition is specified at x equal to 2. So in that case, what we could do is we could use exactly the same method. Okay, convert this into two first order equations. Okay, now to use the Runge Kutta scheme, as you see that we always use a scheme like this, right? Okay, that is, we are starting from y0 and goes to some value, okay, and then go to the next value. This is at x plus x equal to x0, and then go to x0 plus h, right? So we are always using a scheme like that. That is, we are using that y at x plus h as y at x plus 1 by 6 times ky1 plus ky2 plus ky3, okay, so 2ky1 plus 2ky2 plus ky3, y2, y3 and y4, okay, and 1 by 6. That's the kind of scheme we are using. Okay, so to go to x plus h, we need x, right, y at x. Okay, so similarly for z. Okay, so if you want to use that, then if you have boundary conditions specified at the two ends, then we can't use this. Okay, because we don't know if this x value is not specified, then you can't use this. So that case is what you do is you make a guess. Okay, you say that, okay, I make a guess for what the y values are, y0 and y1 are at x equal to x0. Okay, only one is given, other one I make a guess. Okay, and then I go all the way to the other end. Okay, and then I compare the y values I obtained at the other end, satisfy the boundary conditions or not. So that's called a shooting method. Okay, so you make a guess, okay, at the initial value, okay, and then you go to the other end. Okay, so you make a, so if you can't do this calculation because you didn't know what these initial values were, okay, and you knew only one initial value, and the other value was actually the other boundary condition is specified at the other end. Okay, and then I make a guess for this, okay, and then I go all the way. In this particular case, actually, is making a guess for this because I have been given z at the x equal to 2, not at x equal to 0. Right? So I make a guess for this value at x equal to 0, okay, and then I go all the way to x equal to 2, and then I see the value of y I obtain on that side is the same as this or not. And if it not, I make an adjustment into the initial guesses again, and then I go there again to that point. Okay, so in this iterative scheme, I can actually obtain a solution to that equation. A little more tedious, but sometimes not too inefficient. Okay, method called shooting method. So with this, we stop the discussion on the ordinary differential equations. Okay, and we would now go over to a discussion on partial differential equations. Okay, that will be our next topic to look at. Okay. So far we have only looked at equations which are of one variable, derivative with respect to only one independent variable. Okay, we had only everything as a function of x alone. Okay, so both z, that is y prime, and y in this particular case was a function of x alone. But we could have them as functions of many variables, many independent variables. In that case, this differential equation would have derivative with respect to all those independent variables. For example, here is a general partial differential equation. There is a function variable u, which is what we want to find, okay, and u and its derivatives, okay, as what we want to find. So if you want to solve this equation, what we mean by that is we want to find out u as a function of x and y. So x and y are both independent variables. So you want to find u as a function of x and y, and we want to find the derivative of u as a function of x as a function of x and y, and derivative of u as a function of y with respect to x and y. So that will be what we mean by finding the solution of this partial differential equation. So how do we go about doing that? That will be the discussion which we will do now. Okay, so just write the general partial differential equation in this form, okay, with coefficients a, b and c, and there are some constant coefficients a, b and c here, okay. And we have a differential equation of this form, and then some function of and this here some function of u x y, derivative of u, derivative of y, etc. So that's a, if you have a general differential equation of this form, okay. So remember that this can be any function of u x y, derivative of u with respect to x, derivative of u with respect to y, and then we can classify this differential equation into three categories called elliptical, parabolic and hyperbolic. Okay. Not that we need this classification to solve this equation, but we'll try to do one example or look at one example from each of these classes and then how to solve that. And there is no one thing you should keep in mind is that there is no general method for each class of this equation. Okay, so it's not that if you could classify a differential equation into an elliptic form, then there is a partial differential equation into as an elliptic partial differential equation, and there is one numerical method, and then there is a parabolic equation, there is another numerical method, etc. They don't exist. Actually, for the difficulty with partial differential equations is that the method which we use to solve partial differential equation is specific to a particular equation. Okay, there are very few methods which are general enough so that you can use it for a class of problems. Okay. So the technique which you use to solve partial differential equation depends very much on sometimes even the coefficients sitting in front of these derivatives. Okay, the range of those coefficients, etc. We will look at that in the coming classes. Okay, so here let's just see this as three different classes, so that b squared minus 4ac is less than 0 as elliptic. For example, the equation would be Laplace's equation, which you are familiar with in electrostatics, etc. So this Laplace's equation is a case of an elliptic partial differential equation. Remember a, b and c. So a, b and c are the coefficients of the two second derivatives, and a and c as a coefficient of the two second derivatives with respect to variable x and y respectively, and the b is the coefficient of the second derivative, this cross second derivative. Okay, that is del squared u by del x del y. So in the case of Laplace's equation, we have a as 1 and c as 1, b is 0, and f this function is 0. That's what Laplace's equation is, and then we have that as satisfying as this b is 0, so we have ac as less than 0, and a and c are the same sign, so ac is less than 0, so it's an elliptic equation. Now if you had a minus sign here, okay, so that would be a case where again b is 0, but a and c have now minus opposite signs, so it will be a positive case. So that will be a case of a hyperbolic equation. Okay, we'll see that wave equation as an example of. So now if you had one of them 0, that is we had only one derivative with respect to, we only had this derivative, okay, and we didn't have the second derivative with respect to y, but we had some first derivative with respect to y. That is, in this equation, if you have only one of them, a or c as non-zero, and b is also 0, and then with some function here which is non-zero function, in that kind of equations would be parabolic equations. Okay, so as I said, the equation for an elliptic equation is a solution. An example for an elliptic equation is Laplace's equation, and an example for a parabolic equation, and so that is here is a parabolic equation, is a heat equation. Okay, so that is where b squared minus 4ac is 0. Okay, that's a heat equation, actually, or the diffusion equation. We'll look at the solutions of this equation also, okay. And then a hyperbolic equation would be the wave. So there's a three different examples which you would be interested in looking at. Okay, so remember Laplace's equation as an example of elliptic equation, and a heat equation or a diffusion equation as an example of a parabolic equation, and a wave equation as an example of a hyperbolic equation. So one of the things we will always do in the methods which we use here, that is not, as I again repeat, is not a general method for solving partial differential equation. So unlike Runge Kutta scheme, which can be used for a class of the ordinary differential equation, there is no one method to solve a partial differential equation. But the method which we will be looking at here is mostly using replacing the derivatives by its discrete form. Okay, so that is we write an equation of this form, and then we would replace the derivatives by its difference equation. Okay, so that's something which you would be looking at. Okay, so that's we would have, let's say we have an equation of del squared u by del x squared. Okay, it's some function of x, some u and x and y. We don't. Okay, so it's some equation like this. Okay, so u x and y, x is function of x and y. Okay, so and then we would replace this derivative, okay, by its discrete derivative. Okay, that is we would write del u by del x. For example, you could write it as u at x plus delta x minus u at x divided by delta x. So that will be a simple forward differencing scheme. Okay, and similarly we could write del squared u by del x squared as u at x plus delta x, okay, plus u at x minus delta x minus 2u of x divided by delta x squared. Okay, and similarly for y. Okay, and this we'll replace these difference equations into this equation, into a differential equation here. Okay, and we'll convert this differential equation to a difference equation and solve for these u values at various x values and y values. Okay, that's what something we would be doing in as a method for solving partial differential equations. We will not be looking at more complicated methods for solving partial differential equations in this course. Okay, so we'll use such techniques to solve both Laplace's equation and heat equation in the coming few lectures.